everyone. So in the previous lecture we saw how we can simultaneously diagonalize two matrices, but there is a condition that the matrices should be commutative, that is A into B should be equal to B into A. Now is it possible to diagonalize or simplify the matrices when they are not commutating, that is A into B did not be equal to B into A? So this theorem gives us a way to do that. So again we are dealing with two symmetric matrices A and B of the same order. In additional, A is a positive definite matrix. So then the result says that there exists a non-singular matrix P such that P prime AP is equal to I. So up to this point we are in the familiar zone. We know that if we have a positive definite matrix, then we can get such a matrix such that P prime AP is identity matrix. Now here comes the novelty of the result. P prime BP will be again a diagonal matrix where the diagonal elements will be solutions of this determinant of B minus lambda A equal to 0. So this is the interesting part that we have in this theorem. So now let us see how this theorem can be proven. So since A is a positive definite matrix, we can write A as product of M and M transpose, where M is a non-singular matrix. This result you might have studied already. So I don't need to show you from where I got this, but I hope that it's familiar to you. So let lambda be a solution of the determinant B minus lambda equal to 0. Now what we need to prove is that I can create a matrix P such that P prime AP will be identity and P prime BP will be a diagonal matrix of these lambdas. So now the first hint towards the proof is this decomposition of A as M prime. So let us see how it can be done or how to proceed. So because A is M transpose, so pre-multiplying it by M inverse and post multiplying it by M dash inverse, we get M inverse A M dash inverse equal to M inverse M, because A is M prime, M inverse M dash inverse. So now both these will be identity matrices and ultimately this entire product will be identity matrix. So note that when A is equal to M transpose, then we have M inverse A M dash inverse as identity matrix. Now let us consider this determinant B minus lambda equal to 0. This may be intriguing to you as how or from where this condition has come up. Is there a simplification or a justification to this determinant B minus lambda A? Notice that if I had I in place of A, I would have got eigenvalues of B, but that is not the case here. We have a peculiar condition here. So let us see if this peculiarity is indicating to some obvious result. So let us consider this determinant B minus lambda equal to 0. So again we'll because M transpose is A, so and this on this side I have 0. So pre-multiplying it by any constant is not going to alter this equation. So I'm going to multiply it so that I can somehow bring in this A equal to M prime in picture. So to bring in A equal to M prime, this to use this identity, I'll multiply this determinant, pre-multiply by determinant of M inverse and post-multiply by determinant of M dash inverse. So that I can, whatever we did here can be repeated here. Whatever we did here, we will be repeating it here. So this will the first, now these be determinants, product of determinants we have on the left hand side. So that will be like, we can take this inside. So the first term will be M inverse B M dash inverse, and the second term will be lambda being scalar will be kept aside. The second term will be M inverse A M dash inverse. Now notice that this M inverse A M dash inverse is already an identity matrix. We have shown this. So this will be M inverse B M dash inverse minus lambda I. So this is how we get the link. So the eigenvalues So lambdas are nothing but the eigenvalues of M inverse B M dash inverse. So this is how we get the link between these two. So this equation is equivalent to this one. So the solution to this will be the solution to this, or the solution to this will be the solution to this. So this goes on to prove that the lambdas are eigenvalues of M inverse B M dash inverse. So now what? Okay, so let us proceed. So this is what I have stated here. So also note that M inverse B M dash inverse is symmetric. Try taking a transpose and you will immediately realize that it's a symmetric matrix. So bispectral theorem, for symmetric matrices, there exists an orthogonal matrix U such that U prime, the matrix itself U, will be a diagonal matrix with diagonal elements being eigenvalues of the matrix. So let us plug in this matrix here. So U prime M inverse B M dash inverse U will be a diagonal matrix with lambda 1 to lambda n as its eigenvalues. So now we choose, because we are looking for P prime AP equal to I and P prime BP equal to diagonal of lambdas, we choose P is equal to M dash inverse U. So see what happens then. Then clearly U being an orthogonal matrix and A is equal to MM transpose, where A is a positive definite matrix. So all of this indicates that P will be a non-singular matrix. Just consider determinant of P. Determinant of P will be determinant of M dash inverse U, which will, now determinant of U will be 1. So clearly this will be simply determinant of M dash inverse, which is non-zero. In fact, non-zero, and so this makes P as a non-singular matrix. So now let us look at P prime BP. What do we get? So if we choose P as M dash inverse U, then we get P prime BP is equal to U dash M inverse B M dash inverse U. Now, but this is nothing but above matrix, diagonal of lambda i's. So P prime BP is diagonal of these lambdas, and then P prime AP will be U dash. Now A is M dash, so U dash M inverse. So I am just plugging in the value of P prime. So U dash M inverse A M dash inverse U. So this is nothing but M inverse A M dash inverse is already shown to be identity matrix. So this is U prime U, but U dash U or U prime U is simply U being an orthogonal. This will be an identity matrix, and so P prime AP is identity matrix. So this is how we prove this result. So now see, this is how we show that commutating matrices is not unnecessary, is not needed all the time. If we have it, well and good, then we can apply the earlier result. But if we don't have commutating matrices, if we have one of them as a positive definite matrix, still we can diagonalize the two matrices. Now the immediate question that arises in the mind is, can we extend this idea to multiple matrices? What I mean is, can we consider a diagonalization of a bunch or a collection or a set of matrices? So let us see if it is possible. So the first result states that for real symmetric matrices A and B of the same order and positive semi-definite. Now this theorem is just an extension of the earlier result. So instead of positive definiteness, positive semi-definiteness is needed here. Then there exists a non-singular matrix P such that P prime AP and P prime BP are both diagonal. So this is one result, and the next result provides you the extension. So suppose A1 to AK are symmetric matrices of the same order. Then there exists an orthogonal matrix P such that P prime A1P up to P prime A2P up to P prime AKP are all diagonal. Now when can we get this? These are all diagonal matrices if and only if any two of the matrices from this set of matrices A1 to AK, if any two of the matrices are commutating, then we can get this. So AI AJ is equal to AJ AI for any I and J in 1 to K. So let us stop here.